Okay, good afternoon, everyone. Welcome back to our session, the afternoon session, in fact. Hope you enjoyed lunch. Let me ensure that online is on. Yeah. Okay. So we're going to have a hands-on technical experience session with Nicholas Antonillo. He's a technical engagement senior manager for Latin America and the Caribbean at ICANN. All right. So it's just setting up so I can give you a technical demonstration on DNS security basics, DNSSEC, KINDNS, and the KINDNS program. The kind, the kind NS. Okay. Okay. The KINDNS program using DNS. Rather than spelling it out, it is KINDNS rather than ESS. All right, so it's a KINDNS program, a play on DNS. All right, so Nicholas is setting up.
Afternoon, everyone. I hope that we had a great lunch. We have some representatives here. I know that we already established some of our key stakeholders, but just while Nicholas sets up, you ready, Nicholas, or no? You good? Okay. Just to remind some of the persons here about our meeting with ICANN later, we have persons from Flow. Is the Flow representative still here? Or are they not? No? Okay. I'll find out. But I know that Mr. Ferran doing, all right, from Digital. And then we have Mr. Andrew from Islandnet. I'll find out from Flow.
So, I don't have rights to present yet. I'm not co-host.
You're not co-host?
No, not.
All right, I'll have you share the screen. I'll have you make you a panelist.
Okay. It's everything. It's yeah. Yes, just a second. Okay. Send a request to share screen because I'm not allowed to share.
It's
But,
okay.
I already sent a request to share the screen.
I told him to send it to you.
That's it. That's it. Yeah.
Okay. All right. Let me just thank these representatives
Yeah.
first. All right, guys. So before Nicholas begins, we just want to thank a few stakeholders for joining us today. Even though we look a few in numbers here, we have over 90 participants joining us online. I want to thank our audience that's here in person and also our virtual audience. We want to extend thanks to the Ministry of Science, Energy and Telecommunications and Transport. And I see that Ms. Dono is here with us. Thank you for coming. Kadian Smith, Mrs. Kadian Smith Newton, she should also be here. I believe that she's joining us online. Spectrum Management Authority, we're sending their representative here. We have Mr. Carlton Samuels. We heard from him before he presented. Thank you, Carlton. Yes. And we have representatives from, we already called those names, Udacell and Flow, IslandNet, and we have a few more representatives here. So we just want to thank also Jeremy and his team for being here as well and representing. Just a reminder that Flow, Udacell, and IslandNet, we have a meeting, and of course, Jeremy and his team has a meeting with ICANN later this afternoon at 3:30 p.m. Thank you. Go ahead, Nicholas.
You may go ahead, Nicholas.
Get this. Okay. Okay. Hi, everybody. I hope you had a great lunch. Welcome everybody here and everybody online. I'm going to change a little bit what was planned for today, so as to adjust to the timing, to the time left that we have. So this is going to be like 1 hour and 10 minutes something presentation. Okay. For today, what we have in the menu was first go very fast through review on what's DNS, how it works. Then we go through a fast review, maybe not so fast, but a review about what's DNSSEC and how DNSSEC works. Then I'm going to talk a little bit about a program of best practices that are for DNS operators that we call, it's a program that we launched about 2 years ago at ICANN, and it's called KINDNS, KIND, like K-I-N, DNS, which is a kind of broader program of the manners program that was born at ISOC some time ago, like several years before we launched this program. But as manners, as Otis mentioned earlier today, manners is for routing what KINDNS is for DNS. So manners is best practices applied to routing. KINDNS is best practices applying for DNS. And it's the same idea as manners. We don't make standards, we just collect them. And according to what the community believe it's a common practice, we said we collect those, and we set kind of single and common website where you can find all the information, at least for those that are beginning or starting with this DNS journey, okay? to know how to configure, to know about the best practices that you should have in place, that you should implement. Of course, everything, as any best practice, is optional. You can do it or you cannot, but it's better if you do it, okay? Yeah, that's why we normally call them best practices. They are things that everybody agrees that everybody should have deployed in operation. So, and after that, we will do a very fast lab on DNS. The idea of the lab is for you to configure from scratch a DNS resolver and then do some testing. But as we are not going to have so much time to do everything, what I'm going to do is I'm going to introduce the lab. I'm going to show you how to access the lab, and I'm going to also give you the access that is going to be it's publicly available to the lab guide, where it has every step you have to go through in order to configure and then test your lab setup. So, and you're going to have like the rest of the week until Sunday to do it from home, from work, from wherever you want to work, okay? And you can, of course, send me any question, any comment that you have. If you get stuck in some part of the lab, I'm gonna give you my email address so you can send me your comments or questions, and we can do it like that, okay? We can arrange to have that. Yes, also. The thing with that is that the way we set up the lab, it was meant to be only accessed from here, from people that it's within this session, but we can, of course, set up a new lab and allow for a session for students to, for example, a week or wherever you need, and we can, of course, let them do the lab. That will be great to do, okay? So let's talk about that right after the... all right, so very fast. What's DNS? What's DNS? How internet works? In order for a device to be connected to the internet, you need to be able to somehow locate that device, right? So each device connected to the internet, and by the way, when a device connects to the internet, there's no more such thing like I'm connected to the internet. I'm part of the internet. Okay? You're going to connect to the internet, but once you connect, you are part of the internet. Your device is part of the internet with all the good stuff that's in there and all the bad stuff that may happen. Okay? So you are exposed to any cyber attack as well as any device that is publicly connected to that network. Okay? You become part of that big, huge network that we call the internet. And for each device to be able to exchange data with another device in the internet, they need to be uniquely identified. So they need what we call a unique identifier. And there are two flavors of unique identifiers for devices connected to the internet, what we call IPv4 and what we call IPv6, right? So we have devices connected to the internet, each one with an IPv4 and IPv6, or only IPv4 or only IPv6, any of those three combinations. And suddenly, if you want to use a service that is available in the internet or exchange data with a device that is connected to the internet, that it's part of the internet, you will need to know its IP address, right? IPv4 addresses are not so complex to remember. IPv6 addresses are impossible to remember. They are written in hexadecimal. They are like 2 elevated to the power of 128 different addresses. So there's a lot of numbers and letters to remember if you have to remember IPv6, and also there's a lot of numbers if you have to remember IPv4. As well as no one remembers the telephone number of every person that you know. In my case, I only remember two, mine and my wife's, and no one else. But luckily, I have the telephony directory, right? So each time you want to call someone, you just look in the telephony directory, which is an application that lives on your phone or on the cloud these days, you have the number, the name, you know the name, and you have the number. Why? Because the brain, the human brain, easily remember sequence of words more than sequence of numbers. For the normal person, it's easier to remember sequence of words, for example, names and surnames, instead of sequence of numbers, okay? And a proof of that is that you don't remember any number, but maybe 5, 10, 15 numbers, 15 telephone numbers, or far less than that, but you remember the name and the surname of a lot of people that you know, maybe over 100 persons, you know, okay? So the same idea was applied to the internet. People that was developing these protocols, that invented these IP protocols, say, okay, but everybody will have to remember the IP address of a service or of a device. And why not we do the same that was done for the telephony, and we invent something that translates those IP addresses into names that are easily remembered, okay? And so was created what we call the domain name system, the DNS. The DNS is that's the idea behind the DNS. The DNS was created because it was easier to assign names and remember those names than remembering the IP addresses. And what the DNS is for, well, you have the name of a service or of a device connected to the internet. You ask the DNS system, hey, what's the IP address associated with this name? And the DNS will give you back the IP address, which is what you need in order to exchange data with that other device. So that's the main idea behind the invention of the DNS. Okay, and that was mainly why the DNS was invented, to be easy to remember how to locate a device in the internet, in the network. Okay, I'm going to skip a lot of stuff that we already talked about it. So the DNS was created, right? And at the beginning of the internet, there were only 2, 3, 5 devices, computers connected to this network. They just invented the internet, and there were a few devices. And all of this registration, all of this database that associate names with number was done by one person. It was called Jean Postel. Jean Postel was the one in charge of doing what the DNS does these days. Everyone that wants to assign a name to a device, call John and say, hey, John, I want to call my device alpha.com, okay? And John would write in a notepad, with a pen, in a note, they say, alpha.com has the IP 1.2.3.4. Okay, and that was the DNS. And then he would generate a text file that was called host.txt, and will distribute that file to everybody to put that file in the computer. So where you want to contact alpha.com, your computer will look into that file, will find the IP address, and will establish the communications with that IP address. So the information lives in John's notepad and in your computer, okay? But that doesn't scale. It's impossible to think about that way of doing stuff nowadays with hundreds of billions of devices connected to the internet. So that's when the DNS come into play, right? So in the early, at the end of the 70s, beginning of the 80s, the DNS was implemented. The DNS was a standard developed by the IETF, Internet Engineering Task Force, which is the international standardizing organization that standardized all of the protocols that had to do with networking and with how internet works. Like they standardized IP protocol, they created TCP protocol, they created DNS protocol, they created all the email protocol, POP3, IMAP, etc., etc. So every protocol that makes a network run was developed or is developed under the IETF standard process. Okay, and the IETF, it's a kind of independent organization that still lives under the umbrella of Internet Society, okay? I think that's one of the best ways to explain what's the ITF. And then, let's talk a little bit about the DNS architecture. So the DNS architecture looks like this. This is what we normally call an inverted tree, right? An inverted tree because normally, in this world at least, the trees have the root at the bottom and then they grow up, right? This is an inverted tree because the root is at the top and then the tree grows down from the root, okay? And it's a hierarchical database. So this, it's the model of the DNS system. The DNS is just a database where we will put information in it. But it's not a flat database, it's a hierarchical database where at the top of the hierarchy, there is what we call the root, which is that node at the top, which is represented by a dot. The root in the DNS is the only part of the whole DNS that has no name. It is represented by a dot. Any other node, any other part of this database has a name, okay? So if you see, from the root down, we have levels. The first level is called first level in an amazingly innovation in naming. You know, we technicians tend to be that simple. How we call the first level? First level. Okay, let's do. Guess how the second level is called? Second level. Okay. Do you know how many levels can you have in the DNS? Around no, exactly, I think it's, if I don't recall wrong, it's 128 levels. Then we will talk a little bit about that, a little bit more, because 128 levels, while you can have 128 levels, that's useless. You'll see soon why it's useless. But anyway, there has to be a limit, and the limit is that 128 levels depth. Okay, so root at the top of the DNS, okay? The root, any node can have children. How many children? As much as you want. You can have no children. You can have one children, two children, one child, two children, three children, whatever, okay? At the first level, leave all the children of the root, okay? And the root knows what are its children, okay? And let's talk a little bit about the first level. So we have many types of nodes at the first level. Mainly, we are going to talk about two of those types of nodes. One type of node is what we call generic first level domain. By the way, first level domain, it's the same as top level domain. And what's a domain name? A domain name is the name you assign to any node. So you see there at the first level, UK, that's a domain name. You see com, it's a domain name. You see coffee, it's a domain name. So domain names are in the DNS the same as people's names are in the telephony directory. You assign, in the DNS, you assign domain names, you associate domain names with IP addresses, okay? So, types of first or top-level domain names. Generic top-level domains are represented by a G, TLD, and then we have those generic top-level domains are the com, net, org, etc., coffee. And we have what we call the country code top-level domains. Those country code top-level domains are top-level domains, normally formed by 2 letters, and those are assigned one to each country or territory. Which or who defines what's a country or territory? The DNS follows the ISO standard on that. So if there's an ISO definition for a country or a territory, then that country or territory can have a CCTLD, a country code top-level domain. So the one that runs the root will assign a country code, will create a child for each of those countries or territories, okay? As well as the root, the one that runs the root of the DNS will create a child, one for com, one for net, one for org, okay? So we have a lot of top-level domains, generic and country code, okay? Then each of those top-level domains can have children, as much as they want, and they can delegate the administration of those new created subdomains to a different organization. So the DNS is distributed. You see that the DNS is distributed in two ways. It's physically distributed because there's no one single server with all the DNS information. There are hundreds or thousands or more or hundreds of servers all around the world, each one with a small piece of the information from all the DNS. So what's the DNS? The DNS is the collection of all the information that all of those servers have. And those servers, again, there's no one single server with all the information. The information is divided and spread all around the world in hundreds or thousands of servers, okay? Those servers that implement the DNS database are what we call authoritative servers, okay? We will have two kinds of servers in the DNS, two different types of server. What we call the authoritative server, that is one that implements part of the DNS that has the information for that specific domain. And we have servers that we call resolvers or recursive servers. Resolver, recursive server is the same. A resolver, it's a server that it has the function of searching in the DNS system. So if you want to find information, if you want to find the IP associated with a domain name, you are a phone or a laptop, right? And you want to know the IP address in order to access a web page, for example. You are not going to be you looking for the information, asking the different authoritative servers until you find information. You will relay the information to a resolver. The resolver is going to be looking for that information, and once the resolver finds the information, it will return the information to the final user or to the end user, let's say, okay? So there's going to be a communication between resolvers and authoritative servers each time someone wants to find information in the DNS, okay? Good. The other division in the DNS, I mentioned that the DNS is that the information is spread all over the world in different servers, and the other thing that it's distributed, it's the administration. So there's no one single organization administering the whole DNS. The DNS is administered by thousands of organizations. Okay, potentially any domain name can be administered by a different organization. Who decides who will administer a new subdomain that is created? Its parent. So each time a domain creates a new subdomain, each time a domain has a new child, it will decide if it's going to be the same organization administering the parent that is going to be administering that subdomain, or if it's going to delegate the administration to a new organization, okay? If you delegate the administration to a new organization, you are creating what we, in the DNS language, what we call a new zone. So what's a zone in the DNS? Zones are administrative divisions of the DNS. So the distribution of the administration of the DNS is done by creating different zones, okay? Each organization administering one zone, and one zone can have one or more domain names inside, okay? Good. Let's continue with this. So let's go very fast. So we've already talked about what's the DNS, what's the idea behind creating the DNS, what's the architecture of the DNS, and now let's talk very fast about what type of data we will put in that database. So we now know about the database, we know the architecture of the database, now we have to put data in the database, to put data in the DNS. So mainly, as you know, the main information that we put in the DNS is domain names associated with IP addresses. So what's the IP address for a certain domain? That's the information that we put. And the different types of, but that's not the only type of information that we can store in the DNS database. We can store more types of information. Actually, we can store over 80 different types of information. The domain name associated with an IP being only one of those 80, more than 80, okay? The different types of information that we can store in the DNS is what we call a record, a resource record. So what's a DNS resource record or a DNS record? A different type of information that we can put in the DNS. And we assign names to those different types of information. So we have, for example, the type, the record that is used to store the association between an IPv4 address and a domain name is called a record. The record that it stores the association between an IPv6 address and a domain name is called the quad A record, AAAA record, and so on, okay? And finally, just as a fast recap also, let's go through what we call the resolution process. So now we have information stored in the DNS in the form of different records, okay? We want to search for a specific information. We have a domain name, and we want the IP address associated with that domain name, okay? Let's see it with an example. So let's pretend we are in our phone, and we open a browser, a web browser, and we want to access a web page of a site called www.example.com, okay? In order to access that web page, we need the IP address of the web server for that website, okay? Once I have the IP address of the web server, I establish a connection with the web server, I download the web page, and that's all. But I need the IP address of the web server, and I only have the name. I know that it's called www.example.com. So the device will generate a query, a DNS query, a question to the DNS system, asking the DNS, what's the IP address of www.example.com, okay? And again, the device is not going to be searching itself in the DNS system. It's going to rely the query to a resolver. So it will send the query to the resolver. The resolver will say, okay, let's try to find that information. The resolver knows nothing about the answer, so it has to start searching in the DNS tree, in the DNS system, right? Remember that it's a hierarchical model with the top of the hierarchy is what we call the root, okay? So the first node that the resolver will ask for the answer, it's the root. So the resolver will go to the root server and ask the root server, the top of the hierarchy, hey, I want to know the IP address of www.example.com. And the root knows nothing about that. The root doesn't have the answer for that, because the IP address for www.example.com, the server that knows that is the server that holds the information for example.com, and the root is up there at the top of the hierarchy. So the root will answer to the resolver, I don't have the information, I don't know the information you're looking for, but I know my sons. I know the domains that are created right under me, okay, right under the root. So the root will say, I don't have the information you're looking for, but I know what's the IP of the server that has the information for .com, because .com is a child of the root, okay? So now the recursive resolver will go and ask the .com server, hey, .com, tell me what's the IP address of www.example.com. Again, the .com server doesn't have that information. So it will tell the recursive resolver, I don't have that information, but I know who runs, what's the IP address of the server for example.com, because example.com is right under .com, okay? So the .com server sends a response to the recursive resolver saying, okay, this is the IP address of example.com. Go and ask example.com. And then the resolver goes and asks the same question to example.com. And now, in this case, finally, we are asking example.com, what's the IP address of www.example.com? And www.example.com, it's a subdomain of example.com. So example.com has the IP address that the resolver is looking. Okay? Example.com will send back the IP address that the resolver was looking for, and the resolver will send the IP address to the device that formally asked the question, formally sent the query. Okay? And that's the end of the resolution process. In all of those exchanges of information between the recursive resolver and the different authoritative servers, the root, the com, the example.com, etc., every time the resolver gets a response from any authoritative server, it will also store that response in its memory for a while. Okay? Why the resolver will store all the information that it's getting from the authoritative servers in memory? Because if another device or the same device asks the same question again, the resolver will have the information in memory. So it won't have to go again and do all the resolution process. It will take the information from the memory and say, I know that because I asked it before. So this is the answer. And the resolver will very fast give back the answer to the device. Doesn't have to go again through all the resolution process, okay? Why that information is not stored forever in the memory of the resolver? Because if it's stored forever and the information changes, the resolver won't ever notice that change. So the information can be stored in the memory of the resolver, but not forever, just for a while, okay? And that's, by the way, that time window where the resolver will store the information in memory is what we call the TTL of a domain name, time to live of a domain name. That's how long a resolver can store that information in memory. And the memory that the resolver used to store the information is what we, in DNS language, what we call a resolver cache. The resolver cache memory is the place where the resolver temporarily stores the information that it's getting from the authoritative servers, okay? Questions up to this point? Comments? I'm going very fast. Most of you already know about this, okay? So that's how the resolution process works. I have another example here, but I'm not going to comment. So this is the end of the first part of the recap about how DNS works. Now let me send you the second presentation. Beep. So when the DNS was created, when the first right after the DNS protocol was standardized in the IETF, it has some security measures in place, but there were some other security measures that were not part of the original DNS standard, okay? One of those things is we've seen that the resolver will talk to the different authoritative servers, and the different authoritative servers will be sending back to the resolver a lot of information, right? How the resolver can make sure that the information is getting from the authoritative server is the real information. What if someone manages to get into the authoritative server and change the information? If you change the IP address associated with a domain name in the authoritative server, the authoritative server will reply to the resolver will get information that it's wrong. And it's going to be sending a wrong information, a false information to the device, and you will end up accessing a false web page, for example. And what's wrong with that? Well, let's see this example, one of the most common ones, which is one of the most common cyber attacks now these days, which is you want to access your bank account, right? Online. So you put www.mybank.jm, okay? And you will normally be presented with a bank web page that will say login, and you press login and you put your login and your password. And because you care about security and your bank also cares about security, the bank says, okay, it's not enough with the login and the password. We have this two-factor authentication, which is a token that can be generated with a device, with an application. You can get that token by SMS, which is not even close to the best way of doing two-factor authentication. But anyway, it's better than nothing, right? So if you have SMS or nothing, it's better to use SMS. So you have login, password, and two-factor authentication, which is another password that only lives for, let's say, 30 seconds, okay? Okay, great. So if you want to access your bank account, you will be putting your login, your password, and your two-factor authentication, and that's all. You get to your account and you do your stuff, then you log out, that's all. Okay, now, suppose that you're trying to access your web page, and you ask a DNS query, what's the IP of www.mybank.jm, okay? And someone changed that, and a cyber attacker, a criminal, put a false IP address associated with your domain, okay? That can be done by accessing the authoritative server, or when the authoritative server sends the message to the resolver, if someone can intercept the message, tamper the message, change the information there, you will still get wrong information, okay? So either in transit or in the same authoritative server, the information can be modified by an attacker, okay? If you get a false IP address, you're gonna go to a web page that is not your bank web page. But guess what? The cyber criminal, which is also very intelligent, creates a page that looks exactly the same as your bank account page, okay? So you will think you are in your bank account because you put www.mybank.jm and you get to a page that you are familiar with. It's the same page you get every day, so it's okay. Everything is okay, okay? And you put your login, your password, and you type your second factor authentication, and you press login. And then the cyber attacker gets your login, your password, and your second factor authentication. It's okay. The second factor authentication will be valid only for 30 seconds. So the attacker has 30 seconds to do whatever he wants to do or she wants to do, okay? Now, it has 30 seconds. 30 seconds is enough to empty your whole bank account, okay? And that's a common attack. And someone may say, yeah, but there's a protocol that secures the HTTP connections, which is called HTTPS, that relies on a certificate, which is called TLS. And that certificate will certify that the web page that you're accessing is the real one and not a false one. Okay, raise your hand. How many of you check that your certificate you're getting is the real one and it's not a false certificate? So you have the lock that says, yeah, this is HTTPS. Oh, that's perfect, but it's the certificate from the bank or is the certificate generated from the attacker? How many of you do that? Not even me, and I live on this, right? No one does that. So TLS is not enough. If you manage to tamper with the DNS, you are almost 99.9% of the people will be lost and will fall in the trap. The attack will be successful, okay? So what we can do in order to make sure that we are not being taken to a false website? Well, there was a protocol that was designed and created in order to add that type of security to the DNS, and it's called DNSSEC. DNSSEC, it's a security extension to the original DNS protocol that tries to do one thing, which is to authenticate the response from an authoritative server to a resolver. So now, when the resolver gets a response from an authoritative server, if DNSSEC is in place, if you deploy DNSSEC, the resolver will be able to check first, before giving back the information to the client, to the device, it will check if that information is the real one, it's true. If it's the real one, it will give the information. If it does the checking and the checking turns out that the information is false or something is wrong with the information, the resolver won't send back the IP address to the client. It will send an error message telling you that, for example, something is wrong with the DNSSEC. This appears to be false information. I'm not going to tell you a wrong IP, because if I tell you the wrong IP, you're going to be taken to the wrong place, okay? And that's what DNSSEC is, okay? So it's what we call origin validation, okay? DNSSEC allows for validating the origin of the information, validating that the one that is sending the information, the authoritative server that is sending the information to the resolver, is the real authoritative server and is the real information. And that no one tampered with the information when it was transmitted. If someone modifies the information in the middle of the transmission, the resolver will be able to know it also, okay? Good. For those of you that know about routing, there's a protocol that does the same for routing, which is called RPKI. So RPKI is origin validation for routing information. DNSSEC is origin validation for DNSSEC information, for DNS information, okay? Good, how it works. Okay, in order to understand how, this is the example I was explaining. So in order to understand how DNSSEC works, we have to get into some cryptographic theory. Don't worry, you don't have to kind of fasten your seatbelt, because this is not going to be a maths class or whatever, because I'm not an expert in cryptography also. But we have to know a little bit, or just recap or review a little bit of cryptography. So first, what's DNSSEC? Then, from the technical perspective. So from the technical perspective, DNSSEC is no more and no less than a digital signature. Just that, a digital signature. So what we are going to see is how a digital signature works. Once we understand how a digital signature works, we know exactly how DNS works, how DNSSEC works, okay? Okay, digital signature is not that simple, but we will try to explain it, okay? So what's a digital signature? It's a means of verifying or validating data, information, okay? Let's first talk about handwritten signature, right? For what we use handwritten signatures. For example, we have a document, okay? We are sending a document, a formal document, and I say, okay, so the director of the IT institute writes some document, some official university document, has to send the document to the, I don't know, the ruler of the university or whoever, and he, Otis, sign that document and send the document. The one that is getting the document says, this document, who's sending me? Oh, it says that it's Otis, but let's see. Oh, yeah, this is Otis' signature. I recognize it. Okay, I validate the document. Okay, it's from him. That's not an easy task, because how you recognize someone's signature, okay? The problem with recognizing someone's signature is that it turns out that you have to be an expert in calligraphy. I don't know how to say it in English. My native language is Spanish, so sorry. Celia Cruz, the singer, used to say, my English is not very good looking. Okay, for me the same. So it's calligraphy, that's it, thanks. So you have to be an expert in that, okay? That's why when you take a check to a bank, they just use a kind of machine to check for your signature, because you kind of, when you sign up for a bank account, they say, okay, sign here, 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 and they make you sign like 10 times. That's, you know why you are signing 10 times and not only once? Because they have 10 different signatures to compare, because you never sign twice the same way. So they need a lot of cases in order to compare and to make sure that that's a check that you signed. Okay, digital signatures is the same thing, but done by an algorithm. An algorithm that can implement a mathematic algorithm that can implement the same thing, but digitally, not manually. And one of the marvelous and beautiful things about the digital signature is that it's very easy to verify. There's no alternative, or there's no almost no error merging. Okay, it's almost nothing is 100% in probability, but this is almost 100% accurate digital signature compared to handwritten signature. So that's what we use the digital signature. So what's the information in DNSSEC? What's the information that we are going to digitally sign? Well, we are going to digitally sign all the information that goes from an authoritative server to a resolver. So each time an authoritative server sends back information to the resolver, whether it's telling who's the IP of .com, whether it's telling who's the IP of example.com, or whether it's telling the answer that you were looking for, each information that goes from an authoritative server to a recursive resolver, if you have DNSSEC deployed, it's going to be digitally signed. So you get the information, the same information that you get when you don't have DNSSEC, plus the digital signature of that information. And the resolver will have a means to verify that digital signature. If the resolver verifies the digital signature, then the resolver can trust the information. If the resolver is not able to verify the digital signature, means that the information is not trustable. Then the resolver will discard the information and will inform the device, hey, there's something wrong with the digital signature. I'm not telling you the IP because the IP is probably a scam, it's probably a threat. And, you know, so sorry about that, okay? So how it works. In order to explain how a digital signature works, we will go through two different cryptographic concepts, okay? One is this hash function. What's a hash function in cryptography? A hash function, it's a lot of things, but let's try to explain it very, very, very briefly by mentioning one or two or three characteristics of a hash function. So a hash function is a mathematical function, okay? Let's pretend that we have a text. We have a text, okay? We have a letter that we want to apply that hash function, okay? We have a text. It can be one page text. It can be 1 million pages text, okay? We apply a mathematic algorithm process to that document that we have in a digital form. We apply this process called hash, and we have an output, a result. Text, we apply the process, and we have a result, okay? What's the output of the hash? The output of the hash has three main, most important characteristics that we should always remember. One of those characteristics is the length of the result of the output, the length in characters of the output of a hash. Once you decide what's the hash function that you are going to be using, the length of the result, it's always the same. The result, the output is going to be always the same length, the same number how the DNSSEC works. But what's wrong? What's missing? Not wrong, but missing in all my story today. What is missing is that I told you that the public key, it's transmitted from the authoritative server to the recursive server, right? What if an attacker captures the information, captures the signature, captures the public key, change the information, change the signature, and change the public key? You get all the three from the attacker, and all the three will verify. So DNSSEC is useless. No, it's not useless. There's something missing in this story. What is missing is that now all the problem reduces to being able to make sure that the public key is the real one. How a resolver makes sure that the DNS key, the public key, it's the real one. And that's where something called the chain of trust comes into play. What is the chain of trust? So the resolver, before verifying the signature, will take the public key that is getting from the authoritative server and will try to validate the public key first, before validating the signature. How the resolver validates the public key? Well, the resolver will go to the father of the authoritative server. Suppose that we are talking about example.com. So we're trying to validate the public key of example.com. So the resolver will ask .com, hey, .com, you are the father of example.com. Tell me if this is the public key of your son. And the .com will say, yes, that's the public key of your son. How is that the .com tells the resolver that that's the public key? The .com sends the response, sends the public key, signed with its key. So now you have a digitally signed response from the father telling that that's the son. That's the real signature of the son. What's the problem there? That you have to make sure that the father is not lying to you. You have to verify the signature of the father. What do? Now the resolver goes to the father of the father. In the case of the COM, which is the father of the COM, the root. So now the resolver goes to the root and, hey, root server, tell me, is this the public key of the COM? And the root server will tell, yes, this is the power key of the COM by signing the public key of the COM with the root key. Okay? And now there's a new problem. Am I talking to the real root, or is it a fake root server? And how you verify the digital signature of the root? Because the root, guess what? Has no father. It's like Darth Vader in the... No. So how you verify the digital signature of a root that is a node that has no father? You cannot ask the father. And that's when the IETF came out with a protocol and a series of procedures that are called the root key signing process or protocol, which involves something called the root key signing ceremonies. And the root key signing ceremonies are, it's a set of procedures that were created by the IETF and implemented by the internet community in order to preserve the private key for the root zone, so no one will know the private key of the root zone, and also to make sure that every single resolver implementing DNSSEC validation can make sure that that's the public key of the root. And those ceremonies, I'm not talking about that because that will take like 1 more hour at least. But it's mainly the private key for the root zone is stored in a device that it's called HSM, hardware security module, that it's stored it's duplicated. So there are 2 of those. In real, there are 4 of those, and those are physical, like hard disks holding cryptographic information, which is the public key for the root zone, and those devices are stored into a data center in the west coast of the US and another one in the east coast of the US. Then those devices are inside the data center, and they are inside a safe box, which has a combination like the ones that you see in the movies, right? The one of the banks. It's a safe box with a combination. They put this device holding the private key in that safe box. That safe box has another box on the side that has a lot of small boxes inside with a physical key to those. And those physical boxes hold what is called a smart card. So in order for you to be able to activate and use the private key, you need those smart cards that are stored in a different safe box with a physical key. You actually, to activate those devices, you actually need 3 out of 7 different smart cards. So there are 7 smart cards stored in 7 different safe boxes with 7 different keys. Then one of those 7 keys is given to a representative from the internet community, which is called a trusted community representative. Those are selected by ICANN in an open and transparent process, and are people from the community that it's supposed to be trustable, and they give 1 key to each person, and those persons are distributed all over the world. So each time you want to use the private key to sign something in the root zone, you have to call all of those persons to meet in the data center, to open their boxes, take out the smart keys, take out the device from the other safe, activate the device, and sign the root zone, and put back everything in place, and everything goes back to their home. Okay? That's performed 4 times a year. So 4 times a year, the key of the root zone is recreated. Okay? So 4 times a year, all of those have to travel to those places to perform those activities. Okay? And that's everything. It's streamed live on the internet. Anyone can virtually attend those ceremonies. And there's a lot of other systems in place and other measures in place in order to make sure that no one will get access to that, and that the public key will be transmitted to every resolver in the internet in a way that every resolver can make sure that it's the real key. Okay? So now you know that the public key of the root server is the real one. Then you can build the whole chain of trust back to your resolver. Then the resolver can make sure that the public key that is getting from the authoritative server is the real one. Then the resolver can verify the digital signature, and then it can trust. If the digital signature verifies, it may be able to trust the information that it's there on the DNSSEC response from the authoritative server. And that's how the DNSSEC works. Okay, and this is the three results records that are added. Again, the RRSIG is the one that contains the digital signature for each original record. The DNS key is the one where you put the public key for your zone file. And the DS record, it's the chain of trust record. The DS record, it's a record that really lives on the father, and it's the record that the father will send you with the signed public key of its son. Okay? So those are the main 3 records that DNSSEC it's adding to the original records when you don't have DNSSEC. Just a few comments before ending the presentation. And what we are going to do is I'm going to be in contact with Chanel and with Otis. I'm going to be setting up the lab so everybody can access online. I'm going to be sending you the credentials to access the lab and the lab guide script in order for you to follow step-by-step the script, and you will be able to install from scratch a DNS resolver. It's a real one. It's not going to be an emulation. It's going to be a real resolver in the real internet, and you will be able to test that resolver, to send queries, and to get response for any domain that exists out there. And you will be able to do that resolver will have DNSSEC validation activated, and you will be able to check for DNSSEC signed queries and get the response and play with that and test with that, okay? Before ending with this, let me tell you that for DNSSEC to work, there are two sides of the equation that has to do its job, which is the one that is running the authoritative server must sign every record, okay? So the one that runs the authoritative server has to generate a key pair, public key, private key, and with the private key must sign every record and must create all the error side records in its own file. And the one that runs the resolver has a very, very far more simple task, which is has to activate DNSSEC validation in the resolver. To activate DNSSEC validation in the resolver, in almost all of the most common DNS resolver software is one line or one click. One line or one click in the configuration and you are done. DNSSEC validation is activated. When you activate DNSSEC validation, if you get a response that is signed, you will try to validate. If you get a response from someone that has no DNSSEC activated or signed in the authoritative server, if the resolver has DNSSEC activated but gets information that is not signed, it won't be able to verify and it will trust the information and it will behave the same way as if it doesn't have DNSSEC. So to activate DNSSEC doesn't break anything. It's just that now you are able to verify the stuff that comes with a signature, okay? And also, if you deploy DNSSEC in any of the most common servers nowadays, all come with DNSSEC validation enabled by default. Okay, you will see when you do the lab, you will configure the server, and you don't have to configure anything about DNSSEC because DNSSEC will be enabled by default. Because when you install the software, it comes with DNSSEC enabled. Okay. Good. Questions? So, no questions?
I'm going to ask a question. I was going to get one of those. How does DNSSEC prevent rogue DNS servers?
So thanks for the question. DNSSEC can, first of all, DNSSEC is not the single solution to every security problem of the DNS. It's just a protocol that has a solution for a few cases, right? But those are one of the few most common cyber attack cases, and it's been up and running since 2010, so it's trustable. It doesn't generate major or not even minor issues at least at resolver level. So how does DNSSEC prevent a raw DNS server? So a raw DNS server is a false DNS server, a DNS server that has false information, and normally raw DNS servers are used in a cyber attack that was discovered not so long ago by a person that unfortunately passed away not so long ago. He was very young. He was John Kaminsky. He was the one that demonstrated a type of attack that can change the information that the DNS resolver stores in its memory. So it can, an attacker can access the cache of a resolver and change the information in the cache. That type of cyber attack is called cache poisoning, which is to poison the cache, to insert false information into the cache. So the cache poisoning, it's done almost all of the time by creating a raw DNS authoritative server. DNSSEC will verify the digital signature of any response that goes from the authoritative server to the resolver before the resolver puts the information in the cache. So if the information is signed, the resolver will only put that in the cache if it validates. And if it validates, means that it's not coming from a raw server, it's coming from the real server. So if a raw server tries to inject false information in the resolver will be able to say, no, this is not validating, this is not the real signature, and will reject the response. Of course, for that to happen, the domain, the information that is put in the cache has to be DNSSEC signed. So if DNSSEC is not yet deployed for that information, then yeah, you cannot prevent a raw server injecting information. To inject false information in a recursive server is not very easy, but it's also not very hard. The cache poison attack is very simple to perform. It's not very simple to succeed because you have to try. To perform, it's very easy. To generate the attack is very easy. Today, because DNS has other security measures in place, it's hard to be able to perform a cache poison, and even if you don't have DNSSEC, but DNSSEC, of course, it's providing you that security measure, and it's also providing you the ability to separate a false response when you're accessing any website, because you are asking for DNS information, and the DNS information will be validated, and if it's not validating, then you won't be accessing that website. So it also prevents, besides preventing the cache poisoning, prevents like those type of cyber attacks. For example, trying to access bank accounts by using a vector with the most used and the most popular attack vector from an attacker to steal bank accounts, for example, is the phishing. So everything starts normally with a phishing, okay, which is an email pretending to be from reputable organizations trying to make you disclose personal information, login, passwords, etc., etc. So DNSSEC can reduce the amount of effectiveness of phishing attacks, because, again, you are validating all the DNS responses. Of course, it doesn't prevent everything. There are other protocols that you should deploy.
All right, so does the retired versions of the TLS, like TLS 2.0, does it have any impact on DNSSEC?
No, really, TLS, it's a protocol that adds security to HTTPS. Okay. So HTTPS is a secure version of HTTP, and what it adds is a kind of digital signature in the form of a certificate, and TLS is the protocol that is used to transmit those and to validate those certificates, okay? So TLS, TLS1, TLS2, it was in the past TLS, I don't remember the original name. TLS is the evolution of SSL, yeah. Of SSL, right? We don't talk anymore about SSL because we have TLS, okay? But it's a completely different thing. So HTTPS application level. This is at the DNS query level. So should I deploy DNSSEC? Should I deploy HTTPS or both of them? Of course, both of them, because they protect you from different things at different stages, okay? Again, if you always check the certificate, which almost no one does, it will be enough with TLS. Yeah. I would implement DNSSEC also just in case, because normally people doesn't verify the certificates, doesn't check the certificate. And also, there are many places that don't use HTTPS. And with DNSSEC, you can make sure that you're accessing the correct place, even if it doesn't have HTTPS. So you should deploy DNSSEC. Yeah.
Well, I know this session was not on IPv6, PV6, but I'm going back to your first slide on the matter. I realize that many organizations have not deployed IPv6 communicating across the internet. Mm-hmm. Can you say
why they should? Why they should? Okay.
Or why they have not? Or why I know they have not. More secure, but why have they not?
Yeah. So there are many false statements about IPv6. One of those false statements is that IPv6 is more secure than IPv4. Absolutely, completely, definitely false. Nothing to do with security. Because why? Because you can apply a lot of long time existent protocols to IPv4 to make IPv4 as secure as IPv6. So it doesn't go because of security that you must go to IPv6. The basic idea behind IPv6 is that IPv4 addresses got exhausted, right? Yes, right. There aren't more, because internet wasn't planned for these billions and billions of devices connected. So basically not myself, of course, invented IPv6 to just have more addresses, okay? You can operate with IPv4. If you want my personal opinion, I think that IPv4 will be there forever. We will never get rid of IPv4. So let's stop talking about transition. There's no transition. But you will have to deploy IPv6, yes or yes, whether you want it or not. Because why? Because all new devices that will connect will only have IPv6. And then there is an issue with that, okay? It's, okay, will I continue to operate both protocols, IPv4 and IPv6? Everybody in operations knows that if you have to operate two different protocols, it's not twice the money, but it's a lot of money because it's more money than operating one. More money, more knowledge, more people working on that, more headaches, more things to take care of, more security issues because you have all the IPv4 and all the IPv6 security issues. So it's better to operate one. If you are going to operate one, guess what? You should operate IPv6 because it's the protocol that everybody needs to be using if we want to continue to grow the internet. Why they haven't deployed it? It's a funny story, but it has to do with, first, it's very hard to convince the decision makers at a company why IPv6 is important, because it's not about security and it's not about money, but it's about business continuity. My first thing that I worked in operations for over 10 years, and when we deployed the IPv6, that was in year 2004, we told our boss, guess what? You're not going to be able to continue with the business in the future in 20 years. If we were wrong, we should have said in 50 years, but anyway. You are trying to convince them, so you are not saying 50 years, right? You say 20, and it's too much. You should say 5 years. In some years, you cannot continue with your business because the world will be in the need of IPv6 and you won't have it. And guess what? If you decide to turn to IPv6 that day, your learning curve will be too late. So you better start early so you are prepared when you get there. But it's not about money. It's not more profit from IPv6 than from IPv4. It's not about security. It's just about business continuity. Every device that will connect from now on will be on IPv6. You have to be there sooner or later. You decide.
Any questions?
Come on.
Okay.
Hey, that's a question there.
Who was it? Oh.
No, but go ahead.
To ask, how does one deploy DNS security?
How
How is it deployed?
How is deployed? So again, the way that you deploy DNSSEC is if you are running an authoritative server, you have to deal with creating a key pair, what is called a private and a public key. You have to define and design your own way of keeping your private key private. So you will be the only one that knows that key, and you will use that key to sign every record that you have in your zone file. And if you run a resolver, you just want to activate DNSSEC. It's just one command or one click in the configuration, and you are done. And there's almost no impact in the infrastructure in the resolver level between having or not having DNSSEC validation enabled. So the recommendation is always try to enable DNSSEC validation in the resolver because it doesn't change almost no impact in the servers. Mainly because servers nowadays have a lot of memory, have a lot of processors, and can handle a lot of information. Of course, you will be monitoring your servers. Everything needs to be monitoring. And if you see that now you implemented DNSSEC and your CPU or the memory of your server, it's going up, you say, okay, well, this server can handle, or you say, okay, I need a new server, or I need to increase the memory, or I need to add processors to the server. But normally, there's no impact, okay?
Okay, which organizations should prioritize implementing DNSSEC.
So for DNSSEC validation, if you want my personal opinion and organizational opinion, is every ISP, every internet service provider providing their customers a DNS resolution service, so running a resolver, should deploy DNSSEC validation. All of them. Because again, if you don't have DNSSEC validation, it doesn't matter if the authoritative is signed, you cannot verify the signature. So you need to have DNSSEC validation in order for DNSSEC to work, okay?
Okay, any further questions?
Okay, so suppose that there are two issues here. The first is there's something of a performance hit that you take because of the validation steps in DNSSEC. Well, I suspect there's no workaround for that. It's just a part of the.
Yeah, mainly when you activate validation,
Correct.
You are getting, instead of the original response, you are getting a lot more data, right?
Right.
Because what? Because you are getting cryptographic information in the form of a digital signature, right?
Correct.
And you have to verify that. So your server now has to do cryptographic functions in order to
Precisely.
check for that. But the real thing is that DNS information, it's very, very small amount of information. If you compare to any other information transmitted, even web pages, no talking about videos, right? Which is huge amounts of information. So will I have to increase the bandwidth of my server because I enable validation and I have like 3 million customers with 1 million queries per second? No, a gigabit Ethernet standard server connection bandwidth, it's enough. You 100%, 99.9999% that you won't have to increase your bandwidth because of enabling DNSSEC. Will the CPU of your server go up a little bit? Yes, it will go up a little bit. You will probably don't have to do anything, but you are monitoring your servers, right? Far before having DNSSEC enabled. So if you see that the CPU is going up, you plan for increasing whether the CPU or the memory of the server, or increasing the cache memory, because more information is going to be in the cache. That will be something that for sure you're going to do, but you have time, right? If you have a small cache, you'll be doing more queries, but it's not that the system will break, right? So you have time to increase the hash and play with those numbers to see what's the best configuration for you. And another thing that you should do and you could do is to have replicas of your server. So to have by using Anycast, you have as many resolvers or authoritative servers, but in the case of an ISP, for example, if we are talking about validation, it's use of Anycast to have more resolvers, and you have more resolvers. If you add one resolver, that's all, because the increase in memory consumption and CPU consumption, it's going to be far less than adding one more server to your server farm, let's say.
Yeah.
Okay.
So I suppose the issue is that you do take a performance hit, but it's relatively negligible.
Suppose that you get a performance issue, right? Yeah.
Right. Okay. The second thing I'd like to raise is the area or sometimes the need to pass the DS record to a registrar, for example, or
yes.
If so, that's problematic because it's one of the
there's no standard way of doing it.
There's no standard way of doing
yes.
it, and there's some discussions now about various protocols.
Yes.
You can do it manually, but then you run into the possibility of human error, which completely.
Yes. One of the best ways that I found that most registrars and registry exchange that DS, the chain of trust, the DS record is by they ask the customer if you host the DNS of your customers, then you don't have that issue, right? Correct. Because you are the father and you run the son.
And you have the son, so you have both.
Okay, yeah.
So that's not
if you delegate it, that's where the issue arises, right? Okay. One of the best ways of doing that nowadays, It's you ask your customer has a login and password and kind of access with a graphical user interface to your system in order to delegate the DNS and to create records, whatever, right? To create NS record and whatever. So they already have access to your system. So you add something in your system that says, insert copy paste here your DS record. And they copy paste it there. So it's their responsibility. But the good thing about DNSSEC is that when they copy paste that, you can automatically check that that's correct.
Okay.
When they put that, you can do a dig query that checks if that's the real DS record, because you do a dig query asking for the digital thing, for the public key, and you hash that, and you do that, and you check that what is being passing there, the DS record, it's the correct one. If it's not correct, you can instantly say, that's not matching your configuration. So review it, because it's not matching. This is not going to work in real time. So if you check it and it's okay, you can trust that that's the real DS. And now you have the DS. You can put it in your zone, sign it, and put it in your zone. So that's the best and easy way to ask the customer to copy paste the DS record. Yeah, another ways of doing is that there are protocols that are already in place from the IETF. There are like 2 or 3 other ways of automating that, even without the need of asking the person to do that. There's no single solution yet to that, and I think if I would start with DNSSEC, I would start with copy-paste your DS record here, and I will test that at the same time. And once I'm confident with these standards, I can stop doing that and say, okay, now we automate that so we can trust this protocol and use it. But yeah.
Well, I did a bit of research on that because from the registrar's perspective, that is one of the most problematic aspects of implementing DNSSEC.
The transmission of the DS record.
The transmission of the DS record.
Yeah.
And the method you just indicated leaves the responsibility on the customer.
Yes.
Which is good if you're the registrar, because you don't want to mess up your customer's business.
Yeah, and you can verify it.
And you can verify.
So you're not going to fully trust your customer.
So you don't fully trust the customer. The customer pastes the DS record in, and then you do a dig as you've indicated.
Yeah, and you check it. It works. Yeah. Okay.
Of course,
it doesn't work. Okay, do it again.
Of course, that now places an overhead on the registrar. The registrar has to put in a resource, someone or some piece of automation to do that.
Yes, and has to have like someone that program that interface for the customers.
Precisely. So that's an additional piece of work that they
and it also has to communicate that to the registry.
Correct. You have to then communicate that back.
Yeah, but you can have an encrypted channel, like the same channel you use to generate the records for your customers. You already have that.
Yeah.
By using, I don't know, XFR or whatever protocol you use, or no, how it's called, the AIP protocol? EPP protocol. EPP protocol.
EPP
so you can use
protocol,
EPP to transmit the DS record once you have it in the registrar to the registry. Yeah.
I see that IETF is working on some protocol to deal with this issue.
True. Yeah, they are working to easy that and to be automate all that and to make that's the weak part of the DNS.
Yeah, that's a headache for a registrar if you're implementing
and
DNS.
they are trying to solve it. I think that the protocol is already deployed, but I think it's a matter of months before everybody start using it.
It's that far, because I did that. Okay.
Yeah.
Okay.
But yeah, that's true.
Okay, great.
What about its effect implementing DNSSEC and its effect on the latency of the DNS?
Okay. There's another possibility. You know, DNS by default will use UDP protocol at transport level, and if there's a lot of information that doesn't fit into the UDP datagram, it will fall back to TCP. If you have to establish a TCP connection, there's some more milliseconds in that, right? But the real thing is that if everything is configured properly, it won't add that much delay. So because there are so many things that take much more time that the DNS overhead that DNSSEC could add to the DNS. That's, for example, to have a copy of a root server closer to the resolver makes a lot more sense than worrying about the other latency because you deployed DNSSEC. So for those cases that you're going to be using TCP instead of UDP, yes, it's going to be some more milliseconds, but I think almost no client, no end user will notice that. Okay. But it's true. There's slightly more latency if you need to establish a connection than if you just send it through UDP. Okay.
One more question.
Yeah.
Taking the last.
I'm just closing stuff here just to leave fast and not to.
All right.
Okay. Yeah.
Yeah, man. Hello, good day. All right, my question, from an operational place, ISP-wise, I am thinking the concerns and the risk and customers' experience, especially implementing IPsec, moving from non-IPsec. From what I get, it's more the authoritative server. That's the side that you really enable it from. But what if you have that server with tons of zones, so forth? What's the best practices? I mean, we are talking about DNS, so 1 second down or issues that with that migration can become, wide, internet-wise. What's the recommendation and the best steps and experience of persons moving from non-DNSSEC to DNSSEC?
You mean the end user experience or the operator, the ISP?
The ISP.
The ISP.
Right.
Okay. So first of all, you have to feel confident of what you are doing, and first of all, you have to train your people, right? You're not throwing the lions into the people into the lion's cage, closing the cage, and hey, deal with the lion. No. Okay. So capacity building is first. Okay. Then I would go from a kind of sandbox, right? I will deploy DNSSEC and maybe use it first only for internal use, for the computers at operations and internal use. So if you have any issue, you will get it sooner or later, and you run that for a while. Then you can, if you have 500 or 1 million customers, you just do not deploy DNSSEC in all of your DNS servers for everybody. You just do it for a small portion. They won't notice. But if they have any issue, they will, call you. Your call center will be on fire, let's say. But it's better to be getting, clients from a small amount of users than from all of your customers. And once you are okay with that, you are trained, your people is trained, and you feel confident, you start deploying until you have all of your services with DNSSEC validation deployed. But you do it in small steps. You are not in a hurry, so you can do it slowly. Never do that before having all those in place, like training the people and having the people feeling confident about doing it, right? Because you also have to train the people that is in the call center, because they will get, I cannot access my bank. The problem is yours because internet is not working, but internet is working. The problem is that the bank has been attacked and it has a false signature, so you cannot solve it. But the problem is yours because the client will call you, not the bank, right? So maybe you have to call the bank and say, hey, we are having a lot of customers that are not able to access your web page. We've checked it and there's apparently an issue with DNSSEC. So correct your issue in order for our clients to be able to access to you. So you have to be like a person in the middle passing the issues, but that's the story of every ISP, right? Most of the clients you're not responsible, but you have to live with them, okay?
Yeah, this question is probably narrowly focused on running a top-level domain, a CCTLD in this case. What is the level of coordination I would need with ICANN? If it were possible and I was waved a magic wand and all of a sudden .gm was fully implemented DNSSEC, what would happen? Or do I need to, because the root servers obviously need to communicate and are going to be passing, is there any coordination required?
Yes. Yes, yeah, you have to transmit your DS record to the root.
I have to transmit my DS record to you.
So once you sign your JM zone,
right,
before doing, once you sign it, you have your DS record. So you have
Correct.
to transmit that DS record to the root, right?
How do I get my DS record to you?
So, no, luckily,
I don't mean you.
thanks God, I'm not the one that will be getting that DS record. That will be the people from the DNS.
I suppose the question I'm asking is that there must be some, I'm assuming, and I'm pretty sure there is, that there's a formal process
Yes, there is.
for a top-level domain like .gm, if they're going to go this route, that we coordinate that with ICANN.
Sure,
and we have a mechanism for passing.
we can point you and send you and you know, we can go with you through that process for sure. It's not a very difficult process. It's a very easy and very, how do you say, aceitado. It's like oiled process, and everything works perfectly because almost not all of the GTLDs have DNSSEC implemented because it's an obligation.
Right.
Where the you know, the contract between the GTLD
Correct.
and ICANN were amended.
Yeah,
that was an obligation. So now you have to do it because of the contract. It's in the contract. CCTLDs don't have a contract, so you can choose whether to do it or not. But what I mean is that there are a lot of use cases, and it's an easy process. But mainly what you have to do is to transmit the DS record.
Yeah,
once you do
send it.
that, you're done. It's up to you, and then you have the other side of the equation, all the ISPs activating, enabling validation, DNSSEC validation in the resolvers.
Correct.
But that's all the process. See? Okay, thanks very much. And if you have any other question, I will leave you my email in order to be in contact, okay?
All right, thank you, Nicholas. Very good session. Sorry, Rodrigo. Very good session. I'm going to invite Rodrigo to the podium to wrap up today's. I hope Nicholas' presentation don't overshadow Rodrigo's presentation, but let's welcome Rodrigo.
Thank you very much, Otis. And I was very happy to hear that there's a lot of interest around the DNSSEC. This is very important. It's a very hands-on. And please be ready to receive Nicholas' instructions for the lab. So the lab, really at your own pace, you will be able to play with it. As Nicholas says, this is a real live server, so you'll be able to try to do some implementations, and the conversation continues. This is actually one of the main reasons that we're here. We want to really make a difference about it. And I'm going to keep this very short. This is the last presentation of the day. I know many of you are very tired. You've been sitting here for a long time, so thank you for your patience. But I do want, can you, I have a presentation, it's called the NXR, it's the next round. Just that one, please. I'm going to try to keep it very simple, but it's a very important piece of information, and hopefully an opportunity for you guys in Jamaica. We have been providing some hints throughout the day about the next round of generic top-level domains. At this point, you have learned after Nicolas' presentation what a TLD is, right? So you know there are TLDs, top-level domains, how to read a domain name, you know. So you have to read it from your right to left, and whatever is at the last of the last dot is a top-level domain. So .jm is a CCTLD, is a country code top-level domain, and the other ones that we have are generic top-level domains. So what is happening now is that we are opening a new round for those organizations that would like to apply to become a registry of a top-level domain, in this case, a generic top-level domain. So as of today, can we go to the next one, please? Maybe I'm going to, and the next one, please. Okay, So this is what happened from the previous round. Before this previous round, like 10 years ago, there were only about 20 generic top-level domains, and of course, close to 200 country code top-level domains. Perhaps as many countries as we have in the world, but we also have territories. So around 200. But the generic top-level domain space grew from 20 to 1,200 and included different categories of generic top-level domains, new ideas, cities. Can we go to the next one, please? Communities. Okay, that was quick. No. Before that, another one before, and before. Here it is. Yes. Okay. So what happened in the previous run, we received these applications for many cities like .Barcelona, .Paris, .NYC, .Berlin. All of these have been delegated and they're working in the root. We also received brands like .brands. These brands like .Google or .Apple, they are there for the brands to manage internal operations of their own activities, right? They are not intended to register domains. There are many different models. They are for community. So we have the .Catholic, for example, or the .gay, or the we received 2,000 applications, great variety of applications. 1,200 were succeeded, and now we have the opportunity of another window. The difference with this new round, as opposed to the previous one, is that now we have learned how this guy has been doing over the last 10 years. So we can see now actual, real cases. Last time it was a little bit of a bet. We didn't know if a .city was going to be successful or not. Now you can see how they're using them. They're using it. And some of them are really good. I'm going to leave you with some links so that you can see the real cases happening there. But these are perhaps the categories of what you can apply. Good opportunities for cities, regions. This one is important. Users of diverse scripts. We are accepting something that is called IDNs, or internationalized domain names. This doesn't apply to countries as Jamaica, which are based in the Latin script in English. We are lucky, but there are some other geographies like China or Russia and Korea and others that they will benefit from using their own scripts. And now we are accepting those as well. Can we go to the next one, please? Okay, but there is a cost involved. This new window opens in 2026 in April. So you might think this it's a long time. Why are you coming here now and talking about this from now? Because there is a cost involved in applying to become a GTLD registry. And this cost is about $2,000 and $27,000 just for the application. $227,000. Thank you, Albert. For the application only, and you need to prove that your organization has the technical capabilities for running a registry, and you also have the financial, capabilities to run it as well. As you could see from Nicolas' presentation, running a top-level domain is very important. You're running a part of the internet, so it's not trivial. You are not registering a domain. Registering a domain name could be around $20 US, I don't know, from 10 to 100, no? 100 at the most. This is for these organizations to become the registries of a top-level domain. So the reason why we are starting to advertise this now, it is because we have a special program. Can we go to the next one? That is called the Applicant Support Program. So the next slide, please. And the other one. And the next one. Okay. This applicant support program provides two benefits for applicants. So if you qualify and you're a successful applicant of this program, you will get a discount of up to 80% of these evaluation fees. So you, instead of paying the 200,000, you will pay 40,000 US dollars for that. You don't need at this time to disclose or to even know what top level domain you want to apply for. At this moment, this program, by the way, just opened 1 week ago, and the window will be open for 12 months. So it will close the next November. We will be assessing only the organization, whether the organization complies with this criteria and it's eligible for the program. And once you get approved, then by 2026, when this is open, you will need to disclose the TLD of your choice or the TLDs of your choice. But your organization will be already qualifying for this discount. So these are some of the criteria for the applicant support program. We will run a general business due diligence, public responsibility due diligence as well. We will assess that there is a financial need. We are starting to make these presentations and these invitations in the developing world. We're coming to developing regions first before this is advertised elsewhere, because mostly successful applicants for this program, for the applicant support program, will come from the developing world. They need to show that they have the financial need, but at the same time, and this is the trick, they will also need to show that they have the financial viability to run a registry. And if they fall into the eligible entity status, which are, can we go to the next one, please? There are different types of organizations that we are targeting: non-for-profit, non-governmental and charitable organizations, intergovernmental organizations, so the CTU could apply, for instance, indigenous tribal peoples organizations, and here's where it opens a little bit more for everybody. It's micro and small businesses that are social enterprises or that operate in a less developed economy. There are, for example, interest of some ISPs I have heard from other countries in the Latin America and Caribbean region. And can we go to the next one, please? So I mentioned that there is a financial support in the applicant support program. There is a range between 75 and 85% of the discount of the original 200,000 plus evaluation fees, and it really depends on the number of applications that we receive. So if we receive more than 40 applications for this, then you will get only a 75% discount. So it really depends on the money that is available to cover this cost. Bid credit, this is important. Whenever you get 2 GTLDs, I think you talk about the grant program a little bit, or we did before. So in the previous round, we got, let's say, 2 applicants with the same string, .cafe. So what happens here is we try to get them together and see if they can agree to manage the TLD together. But if they don't reach an agreement, then there's a bid, an auction. And with the auction, they will decide who will get that. And with this program, you will get some credit to bid. Then, of course, if you are successful, you will get a reduced or even waived base registry operator fees. These 200,000 US dollars application fee are only for the evaluation fee. You also need to have the running cost of operating cost of running a registry. You will also get non-financial support, which is in-kind support like training materials, mentorship programs, access to an applicant counselor, and a full list of volunteer professionals, service providers. Can we go to the next one? Okay, so I think there's a good opportunity here, even if you think, well, this might be at this time a little bit expensive for what I have in mind, but we are also doing this in advance because it's a good opportunity to get with the right partners, right? you don't need, for example, to have the technical expertise to run a registry because perhaps there is a registry that already exists or a company that already provides this service. I was trying to encourage our colleagues from the .jm in this morning because they have the technical expertise. There's another program which is called the RSP or Registry Service Provider. So if you want to become a backend services for different TLDs, you can get into that program as well. We can talk a little bit about that. The window is open for that program now. But partners, right? Maybe financing can come from a regional development bank or I think there will be creative ideas, but I think it's a good opportunity. It is important to have our region, to have the Caribbean, to have Latin America, have a larger footprint in GTLDs. CCTLDs are well balanced because there are as many as countries are. But in GTLDs, we only have 14 from the Latin America and Caribbean region. And as I said, we have 1,200 in the world. Normally, our region, Latin America and the Caribbean, accounts for 10% about everything, population, GDP, things like that. So we should be expecting to be there around the 100 mark. And I think we have a good opportunity. Last time, we didn't start as early as we're starting now. So hopefully you can also help us spread the word. Hopefully you want to think about a nice domain. In the morning, they threw some good ideas for Jamaica. Some of them really, really cool. Dot reggae or dot Talawa. Yeah, exactly. So just think about it. And yeah, that's it. We will share the presentation to all of you so you have that in mind. Of course, our contact names, we can arrange for extra webinars, things like that. And I think, yeah, that's it for the presentation. And I'm sure we want to close it. I think it's been a long, long day. Thank you very much for your time. Thank you, Otis.
Okay, everyone, it has been a very insightful and informative day. We have come to the end of...
What does ICANN?
Yes, so we have come to the end of a very pivotal moment or time in Jamaica's history, where we're now making connections with ICANN, and of course, with the support of ISOC. We are also seeing where the government is pushing the digital transformation agenda. We're not sure where the smart city project is as yet, but we know that, for example, the Universal Access Fund is implementing programs to ensure that the less fortunate or underserved areas in Jamaica are having or getting access to the internet through hotspots. We know that there is development, e-governance project is getting some traction where taxpayers, you're able to pay taxes online. There's e-banking, of course, but you know that some persons, especially the unbanked and the elderly, are very fearful of online banking. And in fact, it's not only elderly, because recently in a class, in one of my classes, malware analysis and reverse engineering, the students were required to purchase a lab. And one student said to me that they don't even hold a credit card because they don't do online banking. And I found that very weird, you know? I said, but how many of us, how many Jamaicans, or how many people across the world do not even own a credit card? I know the banks have pretty much transitioned to offering, you know, the MasterCard debit Visa card. So you don't necessarily need a credit card to shop online. You're able to use your regular debit card because it facilitates that type of, those types of transactions. But at the same time, there are others who are fearful. And although there are not many instances or publicly known instances of cyber breaches with financial institutions, you know, some persons are still fearful because, you know, you have social engineering attacks that are causing persons to lose access to their data or online banking. However, we're seeing where we're able to build connections with ICANN, for example, in ensuring that we have a robust, resilient, and secure internet. And it will take all of us to ensure that it is so. All right? There's nothing much to be said except a reminder that, you know, we want you to enjoy going through the lab. When do we have? How long do we have? I thought you said Sunday. You said we were saying Sunday. No, but I will say. Extend it. Right. Okay. So I wish you all a great afternoon. I wish you all good success in I'm being reminded that there is refreshment in the break room. Yes, upstairs where we can do further networking, right? And okay, so the network operators, there's a meeting with ICANN in 206 on the same floor as the break room. All right? So that's Flow, Digicel, IslandNet who are here. All right? And please interact with the lab when you do get the login information, right? And that is one thing. Oh, ICANN. You have not introduced ICANN Learn. Well, it's easy, right? So just go and Google ICANN, 2 N's, Learn, right? And you'll be able to learn more about DNSSEC, learn about ICANN, become a member as well. And of course, the same goes for ISOC. ISOC, there's ISOC Learn as well. And it will, of course, you have to be a member first. So I'm expecting. Right. Okay. So, right. But you have to be members of ISOC, and I hope that we'll be seeing some applications. Natalie, do it. I hope we'll be seeing some applications over the next few days for membership, right? With ISOC Jamaica. All right? So we can forge a relationship and, of course, help to support Jamaica's digital transformation. All right, thank you very much, and have yourself a wonderful rest of the day.